Hello, so in this chapter we're going to be looking at elastic strings and springs, and to start off with we're going to be looking at something called Hooke's law. Okay, now before we actually start, just want to remind that this whole chapter, so that includes this video, is going to be year 13 or the A level only. So if you're doing AS further math, you don't need to know this. Okay, no, don't need to bother with this. But if you're doing a full A level, then yes, here we this will be relevant. Okay, so as the chapter suggests, we're going to be looking at strings and springs. So strings and springs are going to be effectively the same thing. They're going to work in the same way, use the same formulas, so we can use them interchangeably, really. Okay. So what we're going to be looking at with strings and springs is when we compress, so when we condense or shorten them, or when we stretch them. Okay, so extend them. As you can see in this little picture here, that's very simply what we're going to be looking at. Okay, right. And so when we do compress or stretch it, that then produces a force in the string. Okay, and the idea is with this force, which for example is tension, which you might be very familiar with, the main idea with a string or spring is that strings or springs do not like being compressed or stretched. Okay, which means in terms of forces, so it produces a force to oppose any compression or stretching. Okay. Okay, so let's have a look at this then. So what I've done here is to really help visualize, because I think with this chapter it's very difficult to visualize sometimes. So I'm going to include various pictures throughout. What we're going to investigate then is very simply, in very simple terms, how the forces or the force in a string or spring works. Okay, so again, the main idea is the string doesn't like to be compressed or stretched, so it kind of opposes it. Okay, so let's have a look at this example first on the left. You can see that this finger on the right is stretching the spring forward, so the stretching is to the right there. Okay, so the spring doesn't like that, so what happens is there's a force inside the spring that acts the other way to the left. Okay, this is going to be a tension force. Okay, so there we are, so it acts the opposite way to the stretching. Okay, then we got this example. This is now compressing. Okay, so what's happening here is the finger on the top is now pressing down on this spring, so the compression is downwards like this. Again, this spring doesn't like that, so it's going to produce a force upwards in the spring to oppose it. Now, when it's compression, it's what we call a thrust force. Okay, so very simply, tension is the technical name when it's tension occurs during stretching. Okay, and thrust occurs during compression. Okay, so you might be very familiar with tension in a piece of string. Tension is specifically when something's being stretched. The thrust force is when it's being compressed. Okay, so hopefully with me here. Now the last example, we've got this tug of war situation. So actually this blue string is being stretched both ways. Okay, what I'm going to do is then split this in half like this. Okay, so we've got two halves of the string. Firstly, if we look at the right, okay, the guy on the right, again the string is being stretched to the right, which means on that half the tension is going to act there. Okay. Now, then on the left, again, the guy on the left is going to stretch the other way to the left, which means on that part of the string, it's then going to act to the right to oppose the stretching. So there we are. Okay. So hopefully that gives just the general gist of how these forces work. How the forces work in a string or spring. Okay, so it just acts the opposite way to what's happened to the stretching or compression. Okay, now we're gonna obviously we're gonna be looking at a formula then to actually work out this force. So it turns out that something called Hooke's law. It gives us a formula to work out the force, the tension or the thrust in the spring. Okay, so it goes like this. So the force in the string T is going to be equal to this lambda x over L. Now, what does that mean? Well, T obviously is my force, so that's going to be tension or thrust, okay? And that's going to be newtons. Now, this lambda here is what we call the modulus of elasticity. Now, that is a number, and it basically just tells me how elastic a spring or string is. So how stretchy it is. Okay, so the higher the number, the more stretchy it is. Now x tells me the how much a spring has been stretched or compressed by. So it's the stretch. So it's what we call the extension. So the extension or compression, and that's a length in meters. Okay, and then L is what we call the natural length of the string. Okay, so that is basically sort of the length of the string normally. Okay, when no force acts on the string, so it's like the original length. Okay, and that's again going to be in meters. Okay, so for example, if we have a look at this top diagram, when it's static, so when there's no forces acting on a spring or string, this is what we call the natural length. Okay, that's all that means, right? Okay, and so this is the formula we're going to be using all throughout this whole chapter. T is lambda x over L. Okay, right. The last thing to note, actually two things. First of all, I'm going to jot down another formula, which might seem a bit obvious, but I think it might help if I write it down explicitly. And that is the total length of a string. The total length of a string or spring, that is going to be the normal length, so the natural length, so the original length, add on the extension. Okay, so when we stretch a string, we add on the extended part of the string to get the total length there. Okay, or instead, if we compress it, so we shorten the string, in that case the total length is going to be the normal length minus the compression. Okay, there we are. Okay, so you might perhaps that might seem a bit commonsensical, but it really might help to write that down. Okay, the last thing to note, you might be thinking, well, how come we didn't use this in normal maths? In normal maths, you hopefully picked up on the fact you'll probably see this word thrown around a lot. Okay, inextensible. We cannot use Hooke's law when a string or spring is what we call inextensible. So what we're going to open up, what we're going to do in this chapter is now look at strings that are extensible, okay, which allows us to use Hooke's law. So what I'm going to say is Hooke's law does not work with inextensible strings. Or springs, okay? So there we are. But yeah, so that's really the main thing we're going to be looking at is T's lambda x over L. Okay. And lastly, I do want to add this point here, this little note. Springs and strings will basically work in the same way. So we can apply the same equations, work out the same stuff. We can do the same maths to it, right? Now, the only difference we need to be aware of between a spring and string is a string cannot be compressed, okay? And you can think about this visually, try to see it. If you have a piece of string, if you try and press into a string to attempt to compress it, what will happen is it will go all floopy, it will go all loopy, it will bend or whatever, but it won't shorten it, okay? So strings cannot be compressed, but a spring can. And so that's the key difference we need to be aware of. Okay, so only springs can be compressed. So a string will never have a compression, but a string will never have a compression, but a spring can. And so effectively a string can only be stretched, okay? But a spring can be stretched and compressed, okay? I just want to raise this point here now, make the point now, because I think there's going to be some questions at the later on in the chapter where this will be relevant. So I do want to make the point explicitly here now. Okay, but there we are. Okay, so we're going to look at some questions then. Here we're told one end of a light elastic string is attached to a fixed point. A force of 4 newtons is applied to the other end of the string as to stretch it. The natural length of the string is 3 meters and the modulus of elasticity is lambda newtons. From the total length of the string when lambda is 13. Okay, so firstly I'm just going to draw the situation. Again, in mechanics you do want to be drawing things out. So what we're told is that one end of a string, it's at a fixed point. Now, what we can do there is, well, let's say we have some little surface. So let's say we have a ceiling and then the string is sort of hanging down. So let's say at this end of the string, that's attached to the ceiling. That's the fixed point, okay? So that's all that means, okay? So the string is attached to something like that. At one end. Now at the what we're told then at the other end, so at the bottom of the string here, we're told a force of 4 newtons is applied to the other end of the string. So what that's going to look like then, if we now if I do another diagram, if we now put on this force, okay, so that's my normal string, but now I'm going to add on the force, okay. I'll do it in a different colour. So it's been stretched. So it's going to be stretching downwards like this. So there's going to be a force at the end that pulling it down, kind of tugging the string down. Okay. And that force is 4 newtons. Okay. So this red bit of the string is my extension. Okay. That's the extra part of the string. When it's been stretched down, okay, and so the initial part in black, the initial part of the string is what is my natural length, okay, and again this will be my natural length as well. So this diagram on the left is where nothing's happening to the string, okay. So hopefully you that makes sense. Now, as for forces, well, again, as we discussed, the 4 newtons force is pulling it down. So this 4 newtons acts downwards. Now, as I said, the string doesn't like being stretched. So the force, the tension force is going to be opposite. So opposite downwards is going to go up the string. Okay, like this. So my tension acts up the string to oppose the downward stretching. Okay, so there we are. Now what we can do first is now actually resolve. We're going to resolve up and down the string. So firstly, my upwards force is my tension T, take away the downward force of 4. That's going to equal mass times acceleration. Now, there's no movement, so actually there's no acceleration. So mass times acceleration, so this is F equals ma. No acceleration means it equals 0. That means my tension force is 4. Okay. But they've not asked me to find the tension, they've asked me to find the total length of the string. So the total length of the string, if I do it in a different colour, is the whole length of the string after extension, right? So that's my total length. So I'm going to need to find the natural length and the extension. Right, but I'm told the natural length is 3 meters. So L for natural length is 3. Which means this is going to be 3 meters. There we are. So I just need to find the extension, okay, the extra bit added. Right, the modulus of elasticity, lambda's 30. Okay. Right, okay. So I'm going to go back to this. So T is 4. Now we're going to use Hooke's law. So T is lambda x over L. This is Hooke's law. So T is 4. By lambda, my modulus of elasticity is 30. Times x. So x then, remember, x is my extension. So actually, this length in red is x. That's the extended part of the string. Okay, so I'm going to call that x. Okay, there we are. Then I'm going to divide by my natural length. My natural length again is 3. And so there, from this I can find x, my extension. So therefore 12 is 30x. So that means x, if I divide by 30, I get 0.4. Okay, but so then the total length of the string, so this is 0.4 meters. My total length is going to be 3.4. So 3 add 0.4. Which is 3.4 meters, and there we are. Okay, so that's the core idea here, right? Let's have a look at another question. Right, so okay, obviously this diagram, I've added this for a reason, to help visualize the scenario. So what is the scenario? So what's happening here is we've got an elastic string. Again, one end is fixed, and then so there we are, one end's fixed. So let's say it's on a ceiling like this, it's going to hang down. Okay, what's going on here is we've got a particle, okay, and it's attached to the other end. Okay, so what's going to happen is if I draw this, when I draw the scenario, when I draw the string with this particle added on at the end, it's going to look like this. So it's going to stretch down because the ball, there's going to be some little ball thing, right? Hanging at the end. Okay? Hanging at the end of the string. And so you can imagine, and this is why I included the diagram. This is essentially what's going on if you're struggling to visualize it. We got some string and then the ball, a ball hanging at the end, stretching the string down. So hopefully you can visualize this. Okay, so again it's going to be an extension. I'm going to call that x. Okay, and then obviously the first part is going to be my natural length, but the natural length is 2. Okay, so hopefully that makes sense. Okay, that's the scenario here. Okay, so we've got some ball that's hanging at the end of the string to stretch it down. Now the particle has a mass of 4, so the particle have a weight. Okay, the weight will act downwards, so there's a downwards force of 4g at the end there. So this weight force is what's pulling the string down. Okay, so it's stretching it downwards. Hopefully happy with that. Now, because the string is being stretched down, then the force in the string is going to act up. That's my tension acting up the string, okay, to oppose the downward stretch. Okay. So what I can do then is, again, I'm going to resolve up and down. So my upwards force is T. Take away the 4G acting down. That's going to equal 0 because, again, there's no acceleration because it's at rest, okay? So that means T equals 4G. Well, actually, if G is 9.8, that means T is 39.2. And there we are. That's my tension force. Right. Okay. But we also know, because of Hooke's law, that T is lambda x over L. Okay, so tension is 39.2. Well, lambda, my modulus of elasticity is 29.4. My natural length is 2. Okay, so lambda 29.4 times my extension x over my natural length of 2. So my sort of original length, right? Okay, so now I can just solve for x. So 78.4 going to be 29.4x. So therefore x is going to be 8 over 3 meters. Okay, so there we are. So that's my extension. That's my extension of the string. So this extra bit in red, the extra part of the string, is 8 over 3, which again happens because the string is being extended or stretched down. So there we are. Okay, so again, hopefully you're happy with that, and hopefully you're happy with how the forces work. Okay, so now we've added some sort of ball at the end of the string, which forces it to stretch down, and so the tension force acts the other way to oppose it. Okay, and so there we are. Right. Okay, now we've got this question. So now we're going to be looking at compression, okay, which works in pretty much the same way. So here we're told a length of an elastic spring is reduced to 0.8 meters when a force of 20 newtons compresses it. Given that the modulus of elasticity is 25, find the natural length. Right, so what's going on here is, again, it's being compressed now, which again will kind of look like this diagram here, just to help visualize it. So again, let's just say normally, again, it's hanging down my spring, and again, that's my natural length. Okay, but then it's being compressed. Okay, so what's going to happen is some just string is going to be the string is going to be compressed because there's going to be a force compressing it. So this force, if you're going to shrink, sort of condense or shrink the spring, there's going to be a force pushing into the spring like this, okay, to compress it. Hopefully happy with that. This force is 20, okay. So this is my compression force. Hopefully you can see it's acting upwards to push into the spring to condense it, okay. And hopefully, so there we are, okay. Right. So there we are. So now this is going to be my total length after the compression, right? This is how much spring I've got remaining after the compression. So this is my total length here, okay? Right. Now again, because now there's a force acting upwards, the spring doesn't like that. It's going to act the other way. So the force in the spring is going to act downwards to kind of push it out. So it's going to oppose the compression. And again, this is my force. This is going to be a thrust force now because it's compression. Anyway, so hopefully happy with that. So now, again, if I now resolve up and down, well, my upwards force is 20 newtons. Take away the tension, the thrust acting downwards. That's again going to equal 0 because there's no movement, okay? No acceleration, so that means t is 20. Okay, but of course we also know that t is lambda x over L. So if t is 20, that's going to equal lambda, which is 25, my modulus of elasticity, times x. Now x is now going to be my compression, so how much string has been compressed here, over my natural length L, and they want me to find the natural length L, okay? So that means 20L, actually, so 20L is 25x. Okay, so we need, so then that means L, if I divide by 20, 25 over 20 is 5 over 4x. Okay, that's about as much as we can do here. So we're good. So if we want to find the natural length L, well, then we're going to need to find x first, the compression. Right, so hopefully with me up to here. So what we were also told is the length of the spring is reduced to 0.8 meters. So that's telling me after compression, the spring is now just 0.8 meters, which is my total length, okay, here. So this is 0.8 meters. Okay. Right. Well, of course, originally it was the natural length L, right? So if I do this, what I've done in purple is the part of the string originally that has been compressed, okay? This is my compression, okay? Which is x, okay? Now, hopefully then you can visualize that the natural or original length L is going to be the compression x added with 0.8 meters. Hopefully happy with that, right? Okay, so again, that's because the natural length, hopefully you can spot it's going to be adding these two lengths, they're the same. Okay, so there we are. Well, then we can rearrange to say that x is L minus 0.8. Well, actually now I can sub that into here. So that means L is 5 over 4 lots of L minus 0.8. Right? So now we can solve for L. So if I expand it, that's going to be 5 for L minus 1. Okay, so then that means that a quarter L is going to equal 1. So therefore L is going to be 4. So that is my natural length there. Okay, so originally the length, the spring was 4 meters. So there we are. That's the natural length. We got this question here. What's happening here is there's sort of two different situations happening. Okay, in the sort of first scenario, again, there's going to be some sort of particle, some ball attached at the bottom of the string. Okay. So we're told, so what's happening is, again, one end is fixed. So again, that means it's attached to some sort of ceiling. Okay. And so my string hangs down, or my spring hangs down. And then there's a particle at the end attached, and that particle has mass 1, which means the mass has a weight pulling it down of 1g, or just g, right? Okay, and again, because that will cause the spring to stretch down to oppose that, the tension in the spring will act up. Okay, so my force T in the spring will act the other way to oppose it. Okay. Now again, if I in terms of lengths, if we're going to add the length on, let's say this part I'm going to do here, let's say that's my original length, so my natural length L, and so this length is my extension X. Okay, hopefully happy with that. And again, my tension force there. Hopefully happy with this setup. Okay. So if I first resolve up and down, again, a T, the upwards force is going to equal the downwards force G. Okay, or T is equal to 9.8. Okay, but of course we also know that T, via Hooke's law, is lambda X over L, right? So that means 9.8. Well, my modulus of elasticity is 20. So 20x over L. Do I know anything about the length? What I do know is the total length of the spring is 1.4. Okay, so the whole length here, the total length is 1.4. Okay, so actually we can kind of come up with a sort of equation separately linking the lengths together, like with the last example. So hopefully you can spot the original length L plus the extension X has to equal the total of 1.4. Okay, so then X is 1.4 minus L. So we can sub that into here actually then. So 20X is going to be 20 lots of 1.4 minus L. So that means 9.8 L is going to be 20 times 1.4 is 28. Take away 20L, and actually we can solve for L here, the natural length. So that means 29.8 L is 28. Therefore, the natural length L is going to be 0.94. And there we are. So I can add that on. So L is 0.94. Lambda is 20. Okay. Right, so hopefully happy with that. So that's happened. So that's when a particle of 1 kilogram is at the end. Okay. Now, what's happening now is that particle is removed and replaced by another particle of 0.8 kilograms. So now we've got this situation here, where again the string is going to hang down. Again, it's going to be a new particle. The mass is 0.8, so the weight of it down is 0.8 g. Again, then the tension in the spring is going to act upwards to oppose the downwards stretch. Okay, the downwards force. Okay, right. Okay, so again, in terms of lengths, I need to find the new length of the spring. Okay, so again, if I, let's say this is my natural length, L, okay, I know that's 0.94. I worked that out previously, right? The natural length is 0.94. Then there's some extension. Now, the extension is going to be different to the first case, because there's different forces, right? So I'm going to call that X2, okay, the extension in this scenario, okay? So there's my tension force. Okay, so hopefully happy with that. And they want me to find the new length. So they want me to find the total length in this scenario here. Okay. So obviously in order to do that, I'm going to need to find the extension. Okay. So hopefully happy with the setup. Okay. At this point, it's just some equations, right? So hopefully happy with that. So again, if I look up and down, my upwards tension force has to equal the downwards force of 0.8 g. Again, no acceleration involved. So that means T, if G is 9.8, T is going to equal 7.84. Okay, and there we are. So again, if T is lambda X over L, that's Hooke's law. So T is 7.84. My modulus of elasticity lambda is 20. So 20 lots of x. Now that's going to be x2, right? That's my new extension, right? As I've said, over the natural length, which is 0.94, right? So now I can actually solve this equation for x2. So so it's 7.36996 by cross multiplying. I get 20x2. Therefore, x2, if I divide by 20, I get 0.36. Actually, 0.37. Okay, there we are. And so that is my extension in this case here. Okay, so x2 0.37. So hopefully then you can spot then that the total length in this case after the extension, the total length of the spring is going to be these two added together, the original natural length and the extension length. So therefore total length, well, the natural length was 0.94, add the extension of 0.37, and that will get me 1.31. And there we are. 2 decimal places. There we are. That is my total length there. Okay, cool. Okay, so we've got this question here. So here we're told an elastic spring of natural length 1.5 meters has one end attached to a fixed point and horizontal force of 6 newtons is applied to the other end and compresses the spring to a length of 1. Find the modulus of elasticity. Right, okay, so again, first we kind of need to visualize and draw what's going on. In this example, it's going to be a bit different to the other ones because now it's not going to be hanging down like this from a ceiling. That's not what's going on. Instead, it's going to be horizontal instead of vertical. So it's going to look like this instead. Okay. Okay. The reason I know this is because it mentions a horizontal force. Okay. So that's right and left rather than up and down. Now, what's going on here is there's a compression. Okay. So what's going to happen here is, and again, I've added this picture here to help you visualize if you're a bit unsure of what exactly what it looks like. What's happening is, again, let's say the originally, right, this is my string. This is going to be my natural length, right? But now there's a force of 1 meter, no, sorry, there's a force of 6 newtons compressing it. So it's going to shorten this the string or the spring, right? And so you can see it's sort of it's compressed and shortened the string. Okay, so now this is my total length, and there's my compression bit which is missing. Okay. Right, so some things. Firstly, I know the natural length is 1.5. So actually the original length is 1.5. I'm also told it compresses to 1 meter. So actually the total length afterwards is 1 meter. That's how much the string is left, or the spring. Again, the same thing. Hopefully then you can spot the compression, how much has been compressed is going to be 0.5 meters. Okay, because 1.5 take away 1 is 0.5. Okay, so I'll add that on. So compression was is 1.5 take away 1, which is 0.5. Okay, now in terms of forces, okay, so it's being compressed by this force of 6. So what's going to happen is there's going to be a force pressing into the spring. That force is 6, and it's going to then act to the left, right, to go into the spring, which means to oppose it, the force in the spring acts to the right. Okay, and that's going to be T. Technically, it's going to be a thrust force because we're dealing with compression here. Okay, so hopefully happy with that. So now, again, if I now resolve forwards and backwards, right and left, my T forces to the right, take away the 6 to the left, that's going to equal 0. There's no acceleration, no movement, so therefore T6, okay? But of course, we also know that T is lambda x over L. So T is 6. My modulus of elasticity is lambda. That's what it wants me to work out. X is going to be my compression now, not my extension. I worked that out. That's 0.5. Okay. And so L, my natural length, again, was 1.5. Okay. So actually I can find lambda quite easily now, right? So 6 times 1.5 is going to be 9 equals 0.5 lambda. So therefore lambda divided by 0.5, I get 18. So 18 there. And the units is newtons, by the way, for modulus of elasticity. As well, but there we are. That is my modulus of elasticity. Okay, so again, hopefully that makes sense. Very slightly different scenario. It's now horizontal, so and I know it's horizontal because it literally mentions a horizontal force. Okay, now we're going to be looking at problems involving 2 strings or springs connected together, right? Okay, so let's have a look at this question here. We're told 2 identical elastic springs, P, Q and QR, each have natural length L, modulus of elasticity 2 mg. The springs are joined together at Q. The other ends P and R are attached to fixed points, with P being 4L vertically above R. Particle of mass M is attached at Q and hangs at rest in equilibrium. Find the distance to the particle below P. Right, okay, so what's going on here? Okay, so we've got these 2 springs, P, Q and QR, and they're connected together. So what's happening is, for the first one, PQ, again, what's going to happen is sort of going to hang down from a fixed point P like this and then it's going to end at a point Q. Then I'm going to do it in red. The other spring in it's going to be like this, and then it's going to end at another fixed point R. Okay, so hopefully you can see that right. So we've got these 2 strings in black and red, and they meet at the point Q. Okay, hopefully happy with that. Now at Q, there's a particle attached at the point Q. So this particle here, or sort of a ball there, and this ball sort of connects the black and the red string together. Now, to visualize this, if it helps, I've got this picture here. It's sort of like a bead, right? So we've got this bead in the middle, and it's between the blue string at either end. That's sort of the situation here. So we've got this sort of particle, this in the middle, and it's it's between 2 strings. Okay. So there we are. Right, now we need to add on our forces. So to help visualize exactly what's going on in terms of forces, let me break it down. Let us consider no particle added on. What's going to happen then in that case? So before we add any particle on, the strings are going to look like this. So again, from P, going to droop down, and then the red string is going to look like this. And you can spot there's a gap between the black and the red string here. Okay, this is before we add any particle on. Now let's say we do add our particle. Okay, so in order to join the black and the red string, then obviously they're not connected at the moment. What's going to happen is firstly the black string is going to extend downwards to meet the particle. Likewise, the red string is then going to stretch up to meet the string as swell, to meet the particle as swell, right? So essentially what's happening is, to sort of help visualize it, you've got this picture here. So in this picture, we've got this man that's pulling two strings together from each end, okay? So you can see that the particle, or the ball, is essentially acting like the guy here. It's sort of pulling these two strings together. So it's stretching the two strings together, okay? And so what that means is, well, for the black string, firstly, it's going to be stretching down to the particle. And then for the red string, it's going to be stretching up, okay, to meet the particle here, okay? Hopefully you can see that, right? So that means in terms of forces, well, firstly, for the force in the black string, if the black string is stretching down, to oppose that, the force in the string is going to act up. I'm going to call that T1, okay, my tension force. Likewise, then for the red string, the red string is being stretched up, so the force in the red string is going to act down to oppose the upward stretch. I'm going to call that T2, tension T2. And so there we are. So those are my two tensions, okay? Again, they're going to be different because the strings are different here, okay? Now, the final force is actually going to do with the weight of the particle, right? Because we're told the particle has mass m, so the weight of it, which will pull it down, is going to be mg, right? So mg there. And those are all my forces. So hopefully that made sense. Okay, so there we are. Now we need to add on some lengths. Okay, so firstly, okay, if this is, so this, let's say that's the natural length of the black string, and then this is the part that's been extended or stretched to the particle. I'm going to call that x then, right? Likewise then for the red string, again, this is let's say this is my natural length. Both have the same natural length here, okay? Both strings have natural length L, right? But then this extension is going to be Y. So this bit that's extended up is going to be what I'll call Y, okay? Hopefully happy with that. Now, what we also know is the total length, okay, from top to bottom. It's 4L, okay? Because we're told P is 4L vertically above R. So from P to R, it's 4L, okay? And so that's everything I need to add on then. So hopefully you're happy with this diagram with the forces and the lengths at play here, okay? I'm going to get rid of this left diagram. I'm just going to work with the right, with this diagram here. So firstly, what I can do now is again look up and down, resolve up and down. Well, firstly, I've got my tension T1 upwards. That's going to equal the downward forces, which is here. So it's the weight mg, add on the tension T2, okay? That's from F equals ma, right? Now, what I can also do then is also use Hooke's law, so T equals lambda x over L. I'll box this. I can use Hooke's law for the black and the red string separately, okay? So firstly, so from P to Q, right, so the black string, firstly, if I use this Hooke's law equation, well, for the black string, it's T1. That's going to equal lambda x over L. Well, lambda is 2mg. That's my modulus of elasticity times the extension of the black string, which is x, over the natural length L, right? I can then do the same for the red string from Q to R, right? And for that, well, the tension is T2. And again, that's going to equal lambda x over L with 2mg times the extension, which is y, okay, over L. Okay, so from these three equations I've got here, what I can do is I know what T1 and T2 are, so I can sub it into here. So therefore, T1, which is 2mg over L, that's going to equal mg add T2. So mg add T2, which is 2mgy over L. What I can do to simplify it, well, I can get rid of the fraction by multiplying everything by L, both sides. So therefore, I get that 2mgx is mgl add 2mgy. Okay, and actually then I can cancel the mg's. So therefore I get 2x is L plus 2y. And that's a lot nicer, right? Okay, but that's really all I can do, except I've also got all these lengths to work with. Now remember, I can consider, if I look at all these lengths, right, I know that all the individual lengths, right, so the individual lengths, that's going to be L plus X plus Y plus L, has to equal the whole length of 4L, the whole thing. So hopefully then you can see, well, if 2L add X add Y is 4L, therefore X plus Y is going to be 2L, right? And so, so we can rearrange. So let's say Y is 2L minus X. So what I can do there is sub Y into the equation I've got here. So then that means 2x is going to be L add 2y, which is 2 lots of 2L minus x. Okay, and so if I expand this, I get L plus 4L minus 2x. I can then add 2x, so then I get 4x equals 5L. Therefore, x is going to be 5 over 4L. And so that is my extension x of the black string. So then if x is 5 over 4L, I can add that on there. Again, the diagram might not be to scale. That's the malloc, just a rough diagram. But that is that's my extension of the black string there, which is x. Well, we're pretty much done because the question has asked me to find the distance of the particle below P. In other words, the distance between P and the particle, which is going to be this purple length here, from P to the particle. Okay. Well, the distance then, well, it's going to be this L add 5 over 4L. Well, L add 5 over 4L, that's going to be 9 over 4L. And there we are. So the distance is L plus 5 over 4L, which is 9 over 4L. And there we are. That's the distance from P to the particle. Cool. Okay, so we've got this question here. So firstly, we need to find the distance of the particle below the ceiling in equilibrium. So what exactly is going on? What do we draw here? Okay, well, we have this spring which has natural length 2a. So this is my spring initially. The length is 2a. So that's before we add any particle on, right? But then we do add a particle on. So this is my spring, and we add a particle in the middle, in the midpoint, okay? Like this. And so what that does is split the spring into two parts, a top and a bottom part. And so that means effectively the natural length halves. So the natural length of each individual, the top and bottom part, would just be A. Okay, so 2A for the whole spring, but then we effectively split it into two like this. So the natural length of the top and the bottom part is just A here. Okay. But that's not all that happens. We then obviously the spring at the top and bottom are also then attached to fixed points like this, and so point A is on the floor. So A is the fixed point here, and B is then at the top at the ceiling there. So hopefully happy with that. Okay. But then obviously what also happens is the particle has a weight of mg that's going to act down. It's going to pull the particle down. So what happens is, initially, yes, we put the particle in the middle, but then once we kind of let go, the particle sort of naturally droop down, again due to the weight. So the particle will then sort of droop down and it'd be somewhere down here, right? Along the spring. So that's where it will sit in equilibrium, right? So there we are. Okay, so then in terms of forces, well, again, the particle has its weight of mg acting down. And then in terms of the two tension forces, so the tension, the top and the bottom part of this spring here, well, for the top part, again, it's the same story as with the last example, where the particle is sort of stretching the top and the bottom strings towards it. So that means for the top string here, it's been stretched downwards towards the particle, and so that means the tension in the top part is going to act up, and this is T1. Then for the second string at the bottom here, again it's been stretched up towards the particle, which would mean that there'd be a tension force acting down. Okay, and that'd be T2. So that's the story, right? The same sort of situation as with the last example. So hopefully happy with that. And then lastly, we need to add our lengths. So obviously the top and the bottom part will have a natural length. So let's say here, this is my natural length. Now the natural length, of course, would be A, not 2A, because again, the spring is split into two parts, the top and the bottom. So the natural length is split up. Okay, and then there'll be an extension of X. Okay, and there we are. Then obviously for the bottom string, then again, that's there's going to be a natural length of the same natural length A, and then an extension towards the particle of Y. Okay, a different extension. Okay, so hopefully happy with that. And lastly, we also know the total height, okay, from top to bottom, because we also know the height of the whole room from ceiling to floor is 5A. So we can add that on as well. And that's everything we can do, right? So hopefully you're happy with this setup here. Okay. Now, we can resolve up and down. So again, I've got my tension force here, T1. And then that's going to equal the downward forces, which is mg, the weight, and the tension T2. There, okay. Again, we equal the top and the bottom forces because it's an equilibrium, so the opposite forces equal one another. Okay, there we are. Then we can also use Hooke's law, and we can use Hooke's law for the top string and the bottom string separately, right? Just like the last example. So firstly, the top spring, sorry, for the top spring. Well, the force is T1 at the top, so there we are. The modulus of elasticity is 2mg times the extension, which for the top part is x, right? Divided by the natural length A, okay? And then we could do the same for the bottom. And so here, well, the force is T2 in that spring. And so again, 2mg times the extension y, okay, over the natural length A, okay. Right. Okay, now we know what T1 and T2 are, we can substitute it into this equation here. So if T1 equals mg at T2, so T1, which is 2mg x over A, equals mg plus T2. And then we can sort of deal with this, right? Let's simplify it. Well, firstly, we can get rid of the fractions by timesing everything by A. So 2mgx equals mga plus 2mgy. Then we can cancel the mg's in all the terms by dividing by mg. So then we get 2x is a plus 2y. Okay, hopefully happy with that. Then I can just rearrange. Let's rearrange for y. So 2y is 2x minus a. Therefore, y is going to be half of this, right? We can expand it. So that would be x minus a half a. And there we are. And so y here, well, I can say y is x minus a half a. Yeah, right? So there we are. Now, the distance they want me to find is the distance of the particle below the ceiling. In other words, they want the distance between the particle and the ceiling. Okay. So they want this distance here. Okay. And then hopefully you can see that the distance we want is a at x. Okay. But I need to find x in terms of a. Okay, I'm going to need to find something for x. Now, to help me with that, I know that if I add all the individual lengths here, that's to equal the total length 5a. So therefore, I can also say that that a plus x plus x minus a half a plus a has to equal 5a. And so then I can sort of solve for x here. So if I simplify it, I get 2x plus 3 over 2a is 5a. So 2x is going to be 7 over 2a. Therefore, I can divide by 2, so x is going to be 7 over 4a. Okay. Cool. So now there we are. We're pretty much done now. So if x is 7 over 4, then the distance we want, which again is a at x, is going to be a plus 7 over 4a, which is 11 over 4a. And there we are. Cool. Then in part B, we've got this weird one marker. So we're told in reality the spring may not be light. What effect will the model have had on the calculation on the distance we found? Just right between the particle and the ceiling. Okay. So here we're told the spring is modelled as light. Now that will be the assumption that'll be the assumption for every sort of spring and string in this chapter. All of them will be light. But what that means is, if you think back from normal maths, light means no mass. And that kind of makes sense sort of in real life. If something is light, it's not heavy, right? So there we are. Which means if it had no mass, so if a spring is not light, it will have mass. And therefore, it would also have a weight, okay? Therefore, the spring would have weight as well. Obviously, that's because weight is mass times g. So if we have a mass, then there's a weight that exists, okay? Now, because if the spring has a weight, well, every weight force acts downwards, right, due to gravity. Which would mean the particle then, if we add in another force downwards, it's going to sort of like push down the particle even further down, right? So what that would mean is, therefore, the particle would move further down the spring, okay? And so then what that would mean is, as a result, the particle is further away from the ceiling. So that means the distance would increase. So the distance from the ceiling would increase. And there we are. Okay, got this question here then. Okay, so again, it's going to be a similar situation to before. What's happening here is, again, they've got this string hanging down and then the particle at the end. I know it's going to look like this because we're told a particle is hung at the end here. So the end here is going to be D, right? So what's happening is, essentially, at the top end is going to be A. That's the fixed point. So A is the fixed point. And so we've got basically two strings connected together again, AB and CD. So what's happening is, the first string is going to hang, it's going to go down to a point B, okay? Then that's when the next string comes in. I'm going to do that in red. And then that's going to go, well, this string then starts at C. So actually B and C are actually the exact same point. And then the red string goes to the point D. Okay? Hopefully with me here. Then at D, that's where the particle is. Okay? Now the particle has a mass M, so the weight pulling it down is mg. Okay? So what's happening here is, this is where it kind of deviates a little bit from the other questions. In the other questions, the particle was in the middle, which split the string in two. But here, the string is sort of connected to make just one long string, because the particle's at the very end. So what happens here is, essentially, there's just one tension force. Obviously, it's going to act upwards because it's going to oppose the downward stretch. Like this. And there we are. So that means in each of the black and the red strings, the tension is going to be the same. And actually, if we just resolve up and down, we can see that T is indeed going to equal mg. Okay, so there we are. Okay. Now I'm going to add my lengths on. I'm going to add my lengths. So again, firstly, for the black string, again, it's going to be some natural length. Let's say here. So the natural length is L, and then it extends until then it connects to the red string. I'm going to call that extension X, and then likewise for then the red part, again, there's going to be some natural length L, and then there's going to be some extension Y of the red string. Okay, so again, hopefully happy with that. Okay. Right, okay. So there we are. Now we're just going to be using our formula. So again, we already know that the tension in both of them is mg. Again, it's sort of because the force, it's because they sort of act as one, because the force, the particle isn't splitting them in the middle. So there we are. Okay, now I'm going to use T is lambda x over L. And again, for the black string, so from A to B, again, I know that T, which is mg, is going to be lambda. Now, for AB, then the modulus of elasticity is 2mg, okay? Times the extension X over the natural length L. Then, for the string C to D, again, the T is going to equal lambda x over L. T is mg. That's going to equal, well, for the string CD, the modulus of elasticity is 4 mg. And the extension is y, okay, for the red string. And the natural length is L. Yes, they have the same natural length, okay, so there we are. And so then at that point, it's just algebra. So again, I can equate them together because they're both mg, they're both equal. So therefore I can say 2mgx over L is 4mgy over L. And simply, if I just multiply top and bottom by L, I can deduce 2mgx is just 4mgy. And so very simply, 2mg, 4mg gets me x is 2y. So I can cancel it down. Okay. I can cancel the mg's. So 2x is 4y. So then x is 2y. If I just break it down there. So there we are. So that means if x is 2y, we can say x here is, well, 2y, right? So the distance they want the length AD. So they want the this distance here, right? This whole distance from A to D. That's what they want. Okay. Okay, so then the distance then is going to be L at 2y and L at y, right? So L at 2y and L at y. That's going to be 2L and 3y. Well, the issue is I need to find y, well, in terms of L, right? I can only have L involved. I need to find y. So I'm going to have to kind of sort of go back to the drawing board. I can't come up with any other equation. I've already used F equals ma. I've used my two tension equations from Hooke's law, and I'm not given any lengths to work with. Okay, these are the only lengths I'm given. Okay, so if I look at the equation with y, if I stare at this one, I can actually simplify it. So I can say that if I do it in red, if I get rid of this, I can say that mgl is 4mgy. And so then the mg's cancel, so therefore L is 4y. So therefore y is a quarter L. And now we got somewhere. Okay, cool. So now I can work out the distance in terms of L. So now 2L and 3 lots of a quarter L. So 2L and 3 over 4L gets me 11 over 4L. And that is my distance from A to D. Okay, now we're going to be looking at problems where things are at an angle now. Okay, so we've got this question here. So here we're told one end, A, of a light elastic string AB of natural length 0.6, modulus of elasticity 10, is fixed to a point on a fixed rough plane, inclined at an angle theta to the horizontal, sine theta is 4/5. Ball of mass 3 is attached to the end B of the string. Coefficient of friction is a third. The ball rests in equilibrium on the point of sliding down the plane. Okay, so we need to find the tension and length of the string. So what's going on here? So hopefully this one should be a more familiar sort of example, a more familiar situation where we've got a slope. Okay, so I'm going to draw a nice slope here, like this, right? And the angle is theta. Okay, right. So here, now we've got a string on the slope, right? Now we've got now one end A is fixed. Okay, so let's say A is there. Okay, there we are. And so it's the string Well, the other end of the string have a ball. Okay, that'll be the point B, right? That's AB. And no, it's going to be the other way around. It's going to be the other way around. The ball needs to be down. It needs to go down the slope because we're told the ball is sliding down the slope, down the plane, right? So actually what's going to look like is A is going to be the fixed point up the slope, and then the string's going to hang down, and then the particle at B. Hopefully that made sense, right? Because I'm told the ball is sliding down. Okay, so the ball needs to be at the further end of the string, okay, for this to make sense. Okay. Hopefully happy with that. Now we need to add our forces on. Well, firstly, the ball has a mass of 3, which means the weight is going to be 3g, which is going to act downwards like this. But of course, with these sort of problems with slopes, again, we need to split up the weight like this. So this is also theta, so this is going to be 3g cos theta, and that's going to be 3g sine theta. Okay, so that's the weight. There will also be a reaction force, right, because it's on a surface. So there we are. Now, let's discuss tension. Okay, now think about it. The particle wants to move down, so that means the string is being stretched down. The string is going to be stretched further down, which means the tension is going to act up the string. Okay, so there we are. Then lastly, we have friction. Now that's the friction of the particle. Now again, if the particle's moving down, friction acts the opposite way. So friction will also act along there upwards. And that's all my forces. Hopefully happy with that. Right. Now, I'm going to note that mu is a third. Okay. So that's F of it. Now, we need to find the tension here, the tension in the string. So, really at this point, once we've labelled our forces, hopefully, again, you're happy with this diagram here. It's just standard procedure. We've dealt with this even in the last chapter, in the work and energy and power chapter, and even in A level, in normal maths. What we can do is start to resolve stuff, okay? So, firstly, what I can do is firstly resolve in this direction, so perpendicular to the slope. So firstly, we got the reaction force acting that way. Then the opposite is going to be the 3g cos theta, okay? And there is no acceleration involved, so it's going to equal 0. So therefore R is 3g cos theta, okay? But we want an actual number for R, so that's going to be 3 times 9.8 for G. But we need to find something for cos theta. Now, we don't have an angle for theta. We only know what sine theta is. Okay, that's 4/5. But hopefully you're familiar with how we can sort of obtain cos theta from this. We don't need to find theta directly by doing inverse sine. What we can do instead, the more sort of proper way, again, if we draw a triangle, the same angle theta, but if we consider SOHCAHTOA, well, if we stare at it, this numerator 4 has to be the opposite, which would be here, and then the hypotenuse would be 5. Okay, therefore we can deduce the adjacent side by Pythagoras. So root of 5 squared take away 4 squared, it turns out to be 3. That's my adjacent side then, right? So therefore cos is going to be adjacent over hypotenuse, so that's 3 over 5. And there we are. So cos theta is 3/5. Okay. And so now we can deduce the reaction is going to be 17.64. Okay. Now, immediately, because I also know the coefficient of friction, I can work out the friction, because I know that F equals mu r, right? Therefore, F is going to be a third times r, and that will get me 5.88. And there we are. Okay, so that's my reaction and friction. Then I can lastly find the force T here by now resolving along the plane, so in this sort of direction. So my force is sort of up the plane, up the surface, up the slope. That's going to be the force T, right? And the force F, the friction, they both act up the slope. So there we are. So T plus F. Then the sort of force in the opposite way is again this 3g sine theta. Okay. Hopefully you're familiar with that from probably other examples you've done before. Again, that's going to equal 0. There's no acceleration here. Okay, so if I rearrange this, so T is going to be 3g sine theta minus F. Okay, so T is going to be 3 times 9.8 for G times sine theta, which is 4/5. Okay. Take away F, which was 5.88. So therefore, T, my tension, is going to be 17.64 newtons. Okay, and there we are. Okay, then I need to find the length of the string. So again, the whole length here. Okay. So, again, the string is being stretched down, okay? Which means it's going to have some natural length and an extension. So let's say, there we are. Let's say this is my natural length, L, and then my extension, X. Now, I know my natural length, I'm told, is 0.6. And the extension, X, I don't know, but I can work it out. How can I work it out? Well, this is where Hooke's law comes in. So T is lambda X over L. I know T is 17.64. It's going to equal lambda. The modulus of elasticity is 10 times X over 0.6 for the natural length. So therefore I can solve for X. So that means 10.584 is 10x. Therefore, X, my extension, is going to be 1.0584 meters. Okay. But they've not asked me for the extension. They've asked me for the length. So that's the total length. So that's this whole length here. So hopefully then you can see the total length of the string is going to be the natural length 0.6 add the extension 1.0584. So that would be 1.6584. And there we are. Cool. And then we got this final part here. We're told if mu is greater than a third, without doing any further calculation, state how your answer to part AII would change. So how would the length of the string change if the coefficient of friction is bigger? Okay, there's sort of two ways I guess you can think of this. You can think of this just mathematically. So if mu is greater than a third, okay, well, what equation involves mu? Well, it's F equals mu r, right? Where did I do F equals mu r? Here. F equals mu r. So if mu is bigger, that means the friction would be bigger, okay? Then F would increase. So my friction force. So then if F increases, well, then my tension here my tension equation here subtracts the F. So if I'm increasing F, I'd have to decrease the tension, right? So T decreases because we're decreasing by a larger number, because we're subtracted by a larger number, right? And so T decreases. Okay, well, again, then by Hooke's law, X would decrease as well. Okay. But X is the extension. So the extension is decreasing. That means the total length decreases. So therefore our answer will be lower. Okay, that's from a mathematical lens, right? But sort of the logic behind it, right, is again, if the coefficient of friction is bigger, that means the slope has more friction, right? It's more sticky. So if you think about it, if the friction is bigger, there's more opposition to the particle moving, so the particle won't move as far. Well, therefore, the particle doesn't move as far, then it won't extend the string so much, so less length. And there we are. Okay. Then we've got this question here. First of all, I'm just going to draw out the diagram to be a bit bigger. Okay, there we are. So we have an elastic string, natural length 2, modulus of elasticity 98. The mass is 4. Basically, pretty much everything's on the diagram. So they want me to find the value of theta firstly. Okay, so the angle theta here. Now, what's happening here is, this is my string here, right? Okay, and obviously this is my fixed point of the string. But you can see the difference with this example compared to the others is it's not completely vertical, so it's not hanging down completely like this, or not like this. It's sort of at an angle, right? So we can do pretty much the same things, but we're going to need to split up the forces horizontally and vertically. Okay. Now, okay, what forces are happening? Well, firstly, again, we've got a particle at the end here. The particle has a mass of 4, which means there will also be a weight of 4g down like that. Okay, we need to add that on. Well, obviously, we're also given this horizontal force of 28 to the right. Okay, now the last force is, as you guessed, the tension. Now, again, this is my string. Okay, and so as you can imagine, the particle here is stretching the string like this. It's stretching the string down, which means the tension in the string will then have to act up it. Okay, so my tension here, T, acts up the string because the string has been stretched down. Hopefully you can see that, right? So those are my forces. But again, this so then the tension force is at an angle. Okay, which means we're going to need to split it horizontally and vertically. Okay, so if I just literally isolate and only draw the tension force like this, so if I only just focus on T, okay, well, if I want to go up the string in this direction to split it up horizontally and vertically, I'm first going to have to move to the left, then up. Okay, hopefully you can see that. So then if I use SOHCAHTOA, I can now deduce that firstly this side to the that's going to be, well, it's the opposite, right? It's the opposite, so it's going to be T sine theta. Okay, then for this side here, this is my adjacent, that's going to be T cos theta. Okay, so here what I've done now is split it up horizontally and vertically, right? So hopefully happy with that. So I've split up the tension at an angle. I've split it into a purely horizontal and vertical sort of component. Okay, and so there we are. Okay, I'm going to add that onto my diagram. Okay, and that's the whole idea. That's the idea of these sort of questions. You want to split up the forces in this way. So that's going to be t sine theta here, and then t cos theta up here. Okay, I'm going to get rid of this here now. So that is my fully labelled diagram. Okay, those are all the forces I need to consider. Okay, now what I can do is resolve. First, I'm going to resolve horizontally, so to the right and left. But firstly, my force to the right is 28. That's going to equal my force to the left, which is t sine theta. Okay, again, it's an equilibrium, which means all opposite forces equal one another. Okay, so therefore t sine theta is 28. I can also resolve up and down. And so if I look up and down, well, firstly, t cos theta here acts up, and that's going to equal the downward force of 4g. Okay, and there we are. So, okay, if I simplify this a bit, if I bring it down here, I have t sine theta is 28, and I also have t cos theta is 4g. Now 4g, if I put g to be 9.8, that's 39.2. Okay, so there we are. These are the two equations I get from resolving. Now, I need I need theta. Okay, I need theta. Okay, so it's sort of like simultaneous equations, right? How am I going to get theta on its own? I need to get rid of the t. Well, what I can do, right, if I call this equation 1 and equation 2, hopefully you're thinking of some trig identities, perhaps. What I can do to solve for theta is I can divide the top equation by the second. And so doing that, I have t sine theta divided by t cos theta equals 28 divided by 39.2. And so what we get then is where the t's cancel. So we get sine theta over cos theta. But what's sine theta over cos theta? Well, hopefully from year 1 pure maths, you'll remember that tan theta, right? So tan theta is 28 divided by 39 over 0.2, and that would be 5 over 7. Now, now we can easily get theta by doing an inverse tan. So inverse tan of 5 over 7 gets me 35.54 degrees. And there we are. That is the value of theta. Okay. Then for part B, they want me to find the length OP. Okay. Now I should say again, O is here and P is there. So in other words, they want the length of the string. Okay, because the string is OP. Right. Well, actually, if we go back to our simultaneous equations here, I know what theta is now, so I can find T, the tension. I'm going to sub it into the first one. So T sine theta, T sine theta is 28. Therefore, T is going to be 28 divided by sine theta. But I know theta is 35.54. So therefore, I get T to be 48.17. Okay. And there we are. Now, why is the tension helpful? Okay, well, hopefully you're thinking, well, the other thing I can use is Hooke's law. So T is lambda x over L, right? Now, again, T, which we just worked out, is 48.17. Now, lambda, the modulus of elasticity is 98 times x over the natural length, which is 2. Okay. So I can solve for x, right? So x, the extension, I can solve for that. So that means 98x is 96.346, blah, blah, blah. Therefore, if I divide by 98, I get x to be 0.983 meters. Okay? And there is x. But that's my extension. So therefore, the length of the string, which in other words is the length O to P, that's going to be the natural length added with the extension. Now again, the natural length is 2, so that's going to be 2 add x, which is 2 add 0.983, which would be 2.983. And there we are. That is my length there. Cool. So yeah, so that's sort of the main idea, right? So when we got a force at an angle, so if we got a tension at an angle, we can split the tension up in this way. So horizontally, vertically, right? Okay, so hopefully happy with that. Okay, then we've got this question here. So here we're told an elastic string PA has natural length 0.5 and modulus of elasticity 9.8. The string PB is inextensible. The end A of the elastic string and end B of the inextensible string are attached to 2 fixed points. On the same horizontal level, the end P of each string is attached to a 2 kg particle. The particle hangs in equilibrium below AB, with PA making an angle 30 with AB. And PA perpendicular to PB. Okay, so how on earth are we going to draw this situation and what exactly is going on here? Right, so again, firstly, we've got 2 strings again. We've got a string PA and then a string PB. And they're connected at P, right? Now, okay, so one string has an end A and the other has an end B. And what we're told about these 2 points is they're on the same horizontal level. Okay, so that means A and B are going to sort of look like that. They're literally on the same level then, right? And then we're told at P, there's a particle at P, right? It hangs at point P below AB. So the particle hangs below AB. So the particle is going to be like somewhere down here, right? Where it's literally below the line AB. Okay, hopefully happy with that. And so actually then we get a sort of triangle, right? If we connect these together. So there we are, right? Okay. And then we're told that PA, the side PA, makes an angle of 30 with AB. So this angle here is 30 between AB and PA. And PA is perpendicular to PB. So that means between PA and PB here, it's a 90-degree angle, right? Great. And that's it. That's where all the points are here. Okay. Now, what we've effectively got then is we've got this string PA and the string PB, and again you can see they're connected together by this point P here at the particle. So if I draw a dotted line, that just represents the line AB. So you can see we've got this triangle here, but these 2 sides are the 2 different strings, PA and PB. Hopefully happy with that, okay? So I guess to really visualize what's going on here, what exactly is going on, like physically, right, intuitively, I've got this big picture here to help visualize what's going on here. And basically it's like a slingshot, okay? As you can see, we've got a slingshot. The ball is being stretched back, so the string is being stretched back, and so there we are. So you can kind of see that here, right? Hopefully you can see that here. So pretend like the ball here is like being strung back, okay, like a slingshot. Hopefully you can see that, right? That to help visualize the situation, right? Okay, now in terms of forces then, well, again, as I said, we've got two strings, PA and PB. These are what the sides are. These two sides are the strings, okay? Now, firstly, PA. As you can then imagine, again, like a slingshot, the string is being stretched down in this way, okay? It's being stretched towards P, okay, if we start at A, which means the tension is going to act up like this, okay? Now I'm going to call that T1, so hopefully you can see that, right? Then likewise for the string PB here, so the side PB, again from B it's being stretched down that way towards P, so then again the tension in that string is going to act up towards B, right? And so there we are. Those are the tensions. Hopefully happy with that. And lastly, we need to consider the weight of the particle, right? The particle has a mass of 2, so the weight will act down of 2g, right? And so there we are. Okay, so I've got all my key forces labelled, but because my two tensions here are at an angle, right? They're on a slope. I'm going to need to split them up horizontally and vertically, like in the last example, right? So if I get rid of this 90-degree angle here and I do this, so I literally split into two triangles which isolate the T1 and the T2, right? So firstly, I've got this triangle here. I'm going to do it in red. Oh, in red. There we are. Okay, if I literally just jot down this triangle down here, just copy it. Okay, so this is right angle. So this is going to be 30 degrees, and our force T1 is going to act up here. So if I want to split this up, this force T1 here, okay, firstly I'm going to have to go up like this and then to the left, okay? And so this side then, that's opposite the angle, so it's going to be T1 sine 30. And so this angle is, this side is adjacent, so this is going to be T1 cos 30, okay? So then if I add this to my main diagram here, we're going to go up by T1 sine 30, then to the left of T1 cos 30, and hopefully you can see again that matches the tension force here, okay? So there we are, we split up the tension force here into vertically and horizontally, so up and down, left and right. Right, I'm going to do the exact same then for the other sort of the other tension here. So now I'm going to be focusing on this triangle here. So again, if I copy that out, oh, there we are. Okay, so again, T2 is there, is here. Now I need an angle. Well, actually, if I know that that this is 30 degrees, I also know this is 90. Right, I'm told that's a right angle, which means this is the remaining angle, which has to then be 60, right? Because all the three angles have to add up to 180, right? Well, there we are. So I can note that. So this is going to be 60 here, right? Oh, 60 here, 60 degrees. Therefore, again, if I'm going to go up here, I'm first going to have to go straight up like this and then to the right. Okay, so this then, well, this side is again the opposite. That's going to be T2 sine 60. Okay, and then this side is the adjacent. That's going to be T2 cos 60. Hopefully happy with that. This is all due to SOHCAHTOA, right? And so there we are. If I label that onto my diagram then, so we're going to go up by T2 sine 60 and then to the right by T2 cos 60. And there we are. We now got all the forces just horizontally and vertically like this. Okay, hopefully happy with that. So now that's all the forces fully labelled. And so then what we're going to do is then start to resolve. Okay, so firstly what we can do is I'm going to get rid of this triangle now just to make room. These triangles, so hopefully happy with that again. So if I firstly look up and down, well, firstly the force is acting up. Well, actually it's these two forces here, they both act up. That's T1 sine 30 plus T2 sine 60. Then that's going to equal the downwards force, which is 2G here. Again, they equal because it's in equilibrium. Okay, cool. Actually, I can simplify this then, can't I? Because I know what sine 30 and sine 60 are. And I also know that G is 9.8. So that's going to be, well, sine 30 is a half, so it's going to be a half T1. And then sine 60 is root 3 over 2. So root 3 over 2 T2 equals 2 times 9.8, which is 19.6. So that equation is simplified there. I can also then look right and left like this, horizontally. Well, okay, so my force to the right is this T2 cos 60. And that has to equal the opposite force, which is going to be T1 cos 30. Okay, again, I know what cos 60 and 30 are. So that means, well, cos 60 is a half. So that's going to be a half T2 equals root 3 over 2 T1, because that's cos 30. And there we are. So then what we've got is effectively simultaneous equations I can solve for T2 and T1. Okay. Right, so let's proceed. So again, I'm just going to solve these simultaneous equations now. But firstly, I can double this equation here. So that means T2, if I times everything by 2, that's just going to be root 3 lots of T1. Okay. And so if we're going to substitute that into the first one, so that means a half of T1 plus root 3 over 2 T2. So it's going to be root 3 over 2 lots of a root 3 T1, because that's what T2 is here. That's going to equal 19.6. So now we can solve this for T1, right? So a half T1 and root 3 over 2 times root 3 is 3 over 2. T1 is 19.6. That simplifies to 4 over 2, which is 2T1 equals 19.6. Therefore, T1 is just going to be 9.8. Okay. Well, there we are. So now I know what T1 is. I can find T2. So T2 is going to be root 3 lots of 9.8. So that means that T2 is going to be 16.97. And there we are. Okay, so how's that going to help? How's the tensions going to help me? Because what I want to do first is find the length of PA. Now, that is the length, well, from A to P. So that's going to be this distance here, right? This distance here from A to P. Well, in other words, well, this is the string PA. So in other words, the length from A to P is the length of the string from A to the string AP, right? Okay, so we're going to need to consider the length of the string PA. Okay, so again, I'll make a note of that. This is the length of string PA. That's what I want to find. Okay, now I know the tension T1 of PA. Okay, so now if I now consider Hooke's law, so for PA, Hooke's law, okay, so that's T1, which is 9.8. That's going to equal lambda x over L. Well, for the string PA, The natural length is 0.5, modulus of elasticity 9.8. So lambda's 9.8 times the extension x over the natural length, which was 0.5. Now we can solve for x. So that means that 9.8x is 4.9, therefore x is going to be 0.5. Okay. And that then is the extension of the string PA. Okay. So therefore, the length of the string PA is going to be the natural length, which again was 0.5, added on this extension, which is also 0.5. And there we are. So that's the length of PA, 1 meter. And there we are. Okay, cool. Then in part B, then they want the length of PB. So it's going to be now, it's going to be that length there. Okay. Well, so the length PB, in other words, the length of the string PB. Okay, now, what we need to notice, you might be thinking, well, let's use Hooke's law for PB because I know what T2 is. However, PB is inextensible. If you go back to what I said at the very start, I made a note that if a string is spring is inextensible, we cannot use Hooke's law. Okay, we can only use Hooke's law for elastic strings, which is why we could use Hooke's law for PA, because it's elastic, but we cannot use Hooke's law for PB. So we're going to kind of have to be a bit more sort of basic, right? We're going to need to find the length of PB in another way, and we're going to need to think more basic. We're just going to need to consider this triangle then. If I sketch this triangle out, what we've got is, again, we've got the lengths A, B, then we've got P, but we worked out the length of PA, didn't we? From part A, from part A, the length of PA was 1 meter. So the side of PA from A to P is 1. And we want this length here. We also know that this is a right angle, and we also know that this is 30 degrees. So actually, to find this missing length here, PB, because we know what this side is, AP, it's 1, we can just use basic SOHCAHTOA. We don't need any extra equations here, okay? So here we are. So, okay, this is going to be the adjacent side. And this is going to be the opposite side. This would be the hypotenuse AB because it's opposite the right angle. Okay, remember, make sure you know your side. Again, this right angle triangle looks a bit weird. So hopefully you're aware, you understand how I've labelled the 3 sides here. So now, well, we're going to be using tan because tan is opposite over adjacent. So that means tan of the angle 30 here, where the opposite is what we want to work out over the adjacent, which is 1. So that means my opposite length is going to be just be tan 30 then, right? Which is root 3 over 3. Okay, so there we are. And that's my length then. That's my length. That's the length from P to B, all right? Or as a decimal, root 3 over 3 was 0.577. Okay, and so there we are. That's the length from P to B. Okay, cool. And then in part C, they want me to find the tension in the string PB. Well, actually, we did it because the string in PB is T2 here. Well, we worked out what T2 was, 16.97. So we did that already. So there we are. That's the question done. Okay, so we've got this last question here. So here we're told an elastic string of natural length 2L, modulus of elasticity 4 mg, is stretched below 2 points A and B. The points A and B are on the same horizontal level, with AB equal 2L. Particle P is attached to the midpoint of the string and hangs in equilibrium, with both parts of the string making an angle of 30 with AB. Find in terms of M the mass of the particle. Okay, so it's quite similar to the last question. It's going to be the same sort of diagram. So again, we're told these points A and B are on the same horizontal level. So let's say A's here. Then B would be over here on the same level, okay? And so then what we're then told is the particle is then in the midpoint here, okay? And furthermore, the particle is going to be hanging underneath the line like this, okay? How do I know this? Because I'm told the particle makes an angle of 30 with both parts of the string. So what's happening there is the string is being stretched down like this, okay? Very similar to pretty much the same as the last example, right? And the angle it makes with the line AB either side is 30, okay? So that's the setup here, okay? Again, like a slingshot. Okay, I'm going to add my lengths in because I know that AB is 2L. That might help. There we are. Okay. Okay, then in terms of angle, in terms of forces. Okay, so firstly, again, I got my particle, the mass. But they told me to find the mass of the particle. I'm gonna say the mass. I can't say M. Okay, they've already used M. That's annoying. I'm gonna call the mass K, which means the weight of the particle is going to be down here by kg. Okay. Then in terms of tensions, but again, the same sort of scenario. The string is split into these two sides here. We've got the string AP and the string PB again, right? But they're what's special about this one is they're actually kind of equal because the particle is in the midpoint, okay? Which means the tension forces, again, the tension forces is going to act up the string here because the string is being stretched towards P down here. Okay, and likewise, the tension for PB is going to act up because again, it's being stretched down. So there we are. The tensions are actually going to be equal because it's symmetrical in this case. Okay, because P is in the midpoint, and so the strings are exactly half and half in this particular case. Okay, and the forces will and so the tensions will be balanced, so they'll be equal. Okay, so there we are. Now, if I now further do this again, what am I going to have to do? I have my tensions, but I'm going to have to resolve them and split them horizontally and vertically. I'm going to have to do that. To do that, then, if I consider this, well, firstly, if I resolve this force here, the tension acting up here, I'm going to have to go up and then to the left. Okay, so then this side is going to be T sine 30. And then this is going to be T cos 30. Okay. And then if I do the same for this tension here, well, actually, I'm going to go up and then to the right. Well, actually, if I go up, it's also going to be t sine 30. Okay, and then to the right, it's going to be t cos 30. Okay. So hopefully happy again with how I split up the two tensions here into horizontal and vertical parts. Again, identical to the last question. Okay, so hopefully happy with this. These are all my forces. I can actually also, because it's in the midpoint, I know the whole length is 2L from A to B. The midpoint is L each side. So there we are. Okay. So now let's resolve. Let's firstly look up and down. So up and down. Well, firstly, I've got my two forces up. So I've got t sine 30 and another t sine 30. Actually, I could simplify this to just two lots of t sine 30 because they're the same, right? 2 t sine 30 is going to equal the downwards force of kg. Well, I can actually simplify this because I know that sine 30 is a half. 2t times a half is 9.8k, because g is 9.8. So that means now 2t times a half is just t. So t is 9.8k. And there we are. And then we can perhaps look at resolving right and left, so horizontally. But if we do that, well, the force on the right is t cos 30. That's going to equal the force on the left here, which is also t cos 30. Well, that doesn't help us. It doesn't tell us anything. But it does tell me my forces are labelled right, which is great to know. Also, what this would mean is actually, if you were a bit unsure about the tensions being equal on the left and the right, so if I called this T1 and T2, right, then with this equation, then we would say T1 cos 30 is T2 cos 30. Well, the cos 30s will cancel to get T1 equals T2. So actually, hopefully you can see here then that indeed the tensions on the left and the right side must be equal. Okay. So the only thing I do know really is T, the tension is 9.8K. Okay, so if I have a tension, then it might be a good idea to use Hooke's law, right? T is lambda x over L. Now, where am I exactly going to use this Hooke's law? Okay, well, what's happening here is, again, I have these sort of two. I got these two half strings together, right? So I got half the string from A to P, and then the string from P to B, and these two make up the whole string. Okay. So what I can do, like with the last example, is just consider one part, right? So let's consider just the part from A to P. Okay. So let's just consider this part here, right? Okay. So I'm only going to apply Hooke's law to the string A to P, right? So A to P. Okay, so again for A to P, I have my tension force T. So that means T, which I know is 9.8K, is going to equal lambda x over L. Well, the modulus of elasticity is 4mg times extension x over the natural length. Now, as I just discussed, we're only dealing with one half of the string, okay, from A to P. So we're going to be halving the total natural length, because remember the whole string again goes from A to P, then P to B. I'm only doing A to P here, so it'd be half the natural length. Okay, so it would just be L. So therefore 9.8K lots of L is 4mgx. Okay. And so there we are. Okay, I'm going to need to find the extension X. Okay, I'm going to need to find the extension X for the string A to P. Now again, like with the last example, this length here is the total length from A to P. So this is the total length of the string A to P. So if we want to find the extension of the string from A to P, we're going to need to find this total length here. So let's consider just the triangle here, right? If I do the triangle here, then I'm going to copy this down here. So this is going to be 30. I want to find this length here. Okay, what is this length here? This is A, that's P. This is a right angle. Okay, so hopefully happy with that. So there we are. So I'm going to be using some trig here. But what I also know again is that this length is L. So here is L. So now I'm in a position where I know an angle and a side. So if I use SOHCAHTOA, okay, well this, okay, the side AP here, that is my hypotenuse, because that's facing the right angle. And here, the side L is my adjacent. Okay, so SOHCAHTOA tells me that cos 30, so cosine, is adjacent. So that's going to be L over the hypotenuse, which is what I want to work out, right? In fact, I'll make it more clear. So that's going to be the adjacent over the hypotenuse, which is L over that, which means the length AP, that's going to be L divided by cos 30. If we just rearrange this, right? Okay, so therefore AP, the length AP, well, it's L divided by cos 30. So if we divide by cos 30, we get AP is 2 root 3 over 3 lots of L. Okay, and so there we are. That is my length from A to P here. Okay, 2 root 3 over 3 lots of L. Okay, hopefully happy with that. So that is the total length of the string A to P. But that's the total length. I want the extension of that string, X. So therefore, the extension, okay, the extension X is going to be the total length, which was 2 root 3 over 3L, take away the natural length, which was just L. Okay, that gets me my extension. If I work that out, that's going to be 0.155 lots of L. Okay, and there we are. So now I could substitute that value of X into here. So that means 9.8k lots of L is going to be 4 mg lots of X, which is 0.155 L. Okay. So that means 9.8k L is going to be 4m times g, which is 9.8, times 0.155 L. Now what I can do, I can actually divide by 9.8 lots of L. So I can cancel out 9.8 and L from both sides. So that means I just get K to be 4M times 0.155. And so there we are. We can then deduce that K is going to be 0.62 lots of M. And that is my answer. So the mass, which is K, is now in terms of M here. Okay. And there we are. So again, that's the whole idea. Okay, like with the last example, we can just consider one side A to P, so we can just consider that string A to P there. Okay, and then we can work out the length using SOHCAHTOA, and then go from there. Okay, but that's it. Hopefully that has helped. But I'll see you next time.